All right, line emission spectrum. We're going to talk about energy and electrons and how they travel and light equations and so forth. So energy comes from electrons. Like if an electron is giving off energy, it's falling to lower energy levels. If it's gaining energy, it's traveling to higher energy levels. When we consider it excited, that means it's on like energy level 2 or 3 or 4. When it's at its ground state, that's the lowest it could be. That means closest to the nucleus. When it's not at its ground state, it has potential energy. It has the possibility to come back down to its ground state. And then when we're seeing light, like when you look around and you can see things, it's because there's electrons that are moving within the atoms that are all around you. And those electrons are falling down to ground state and giving off light. That's what we can see. Here's a visualization of that. So if I have, here's a ground state, right, where we're at energy level 1, which is this out right here. It says like n equals 1, so ground state. Here's n equals 2, which is this circle here, n equals 3, this circle here, n equals 4, n equals 5, so forth. So electrons can sort of travel on any of these, what we call like quantized energy levels, and they can fall. So this electron here is going from energy level 5, and it's falling down to energy level 2. When it falls down in energy level, it releases energy. So that's why you see these arrows going out. And depending on how much energy is released, it gives you a different color. So if it's like a smaller, what's that word? Distance. If it's traveling a smaller distance, so this is just from energy level 3 to energy level 2, then I'm going to get like a red color. If it's a further distance, energy level 5 to energy level 2, I'm going to get this like violet color. And then we kind of have colors that range all the way in between. So violet is like our highest energy, and then red is our lowest energy. Let's see. I'm going to play that video at the end of the notes, so if you want to stay on for that, you can. We have a couple of series. The Balmer series is what we talk about for hydrogen, but there's more series as well. I think these are on the next slide. Yes. So here we go. They kind of look like rungs on a ladder where the light is most quantized. It's brightest. And because we see a red color, we know that an electron within this atom is giving off a wavelength that is a red color, which is a lower energy, but it also has a lot up here in the blue range, right? So it's giving off a lot of high energy too. So we can tell where like an electron has been or where it's going based on that, based on what color we see. Every atom has its own set of colors. So this is sort of like the fingerprint for an atom. We can actually calculate how much energy that is based on the wavelength. So these are the two equations that we have. So if I was going to take this red color here and I was going to estimate that it was, 600 nanometers or something, that would be the wavelength. C is the speed of light. It's a constant, which means given the wavelength from the color and giving the speed of light, I could calculate frequency. I could then use the frequency in this equation and multiply it by h, which is Planck's constant here, in order to calculate the energy. So based on the color that I have, which is a wavelength, that's the actual measurement, I can calculate how much energy that electron gave off, and then I can also calculate how far it traveled, like from energy level 6 to energy level 1, or however. I do that by using the Bohr equation. So there's examples of these two equations and this Bohr equation in your digital notebook, but I just wanted to run through it. So change in energy, that's the final energy minus the initial energy. That's what you would see here if I was calculating the energy that it traveled, right? The energy that it traveled tells me how far it traveled. So this energy here is the same as this one here. So I take the negative of the Rydberg constant, which is this number here, and I put it into this equation where 1 over n squared, that's the final energy level, where if that was here and I was going from like 6 to 1, 1 is the final if I started at 6 and went to 1, and 6 would be the initial. So it'd be like 1 squared and then minus 1 over 6 squared. So again, N just stands for energy level. And then here's another little visual. So as I'm traveling from one energy level to another, it's giving off another color. So earlier I said that if I went like one energy level, I would get red. And then I said red was about 600. So here we're showing 657. So based on what color you could see on this visible spectrum, you could kind of estimate it. If you saw like, you know, a turquoisey color, you might pick right here and say, okay, well, that's about 486 nanometers. Maybe you see something that's like this orangish color, and you know that that's 657, you know that that's 486. So maybe this right here is 600, maybe like 590. That's what you would estimate if you saw sort of like an orangey color. So based on the colors, you will predict wavelengths, and then you will use the wavelength to predict energy. I might also have you do it the other way, where I give you an electron path. So I say like energy level 2 to energy level 1, and you would then give me, I would say that, and I would ask you like, what is the color? So you would do this Bohr equation to find the energy, and then you would use the energy to find the wavelength. And then based on the wavelength, let's say you calculated the wavelength and it was like, you know, 434. You would say it's a blue-violet color, something like that. So there's examples of that in the notebook for you guys. Oh, I did those Bohr problems in the notebook as well. So